There is a number that haunts every physicist, every astronomer, every person who has ever tilted their head back on a clear night and stared into the dark. That number is so large, it almost stops being a number and starts becoming a kind of philosophical problem. There are, by current estimates, somewhere between 2 trillion and 3 trillion galaxies in the observable universe alone. Each of those galaxies contains, on average, hundreds of billions of stars. And orbiting those stars, as we have discovered through decades of painstaking observation, are planets. Enormous numbers of planets. Planets in the habitable zones of their stars. Planets with liquid water. Planets with rocky surfaces. Planets that sit at just the right distance from just the right kind of star to make the chemistry of life at least conceivable. When you do that arithmetic, the number of potentially life-bearing worlds is so staggeringly large that the intuitive, almost gut-level conclusion seems obvious. The universe must be teeming with life, intelligent life. Civilizations that have been growing and thinking and transmitting signals into space for far longer than we have, and yet here is where things get genuinely strange. Because despite all of that math, despite all of those trillions upon trillions of candidate worlds, we have received exactly nothing. No signals, no artifacts, no unmistakable signature of another mind reaching out across the cosmos. The silence is absolute, and that silence is one of the most profound unsolved problems in all of science. This is what the physicist Enrico Fermi captured in a single, devastatingly simple question at lunch one afternoon in 1950, a question that has since become known as the Fermi Paradox. If the universe is as large and as old as we know it to be, and if the conditions for life appear to be as widespread as our telescopes suggest, then where is everybody? That question, short as it is, contains within it a genuine confrontation with some of the deepest uncertainties in physics, biology, and the theory of intelligence itself. To understand why finding intelligent life might be genuinely impossible, and not merely difficult in the way that finding a lost key is difficult, we have to start with the mathematics of time. The universe is approximately 13.8 billion years old. Our own sun did not ignite until about 4.6 billion years ago, which means that by the time our solar system was even forming, the universe had already been running for more than 9 billion years. Stars older than ours have had 9 billion extra years to cook up planets, to allow chemistry to complexify, to permit the slow grinding gears of biological evolution to do their work. If life can emerge, and if intelligence is a natural downstream consequence of life, then civilizations older than ours by hundreds of millions, perhaps billions of years, should theoretically exist. A civilization with even a million-year head start on us would be so far beyond our current capabilities that the gap in technology would be comparable to the gap between a modern supercomputer and a stone tool. And yet the sky is quiet. The natural first response to this is to question one of the assumptions in the chain. Maybe the conditions for life are far rarer than we think. This is the heart of what biologists and physicists call the rare earth hypothesis. The idea that while stars and planets are common, the specific combination of factors that allowed life to flourish on Earth is extraordinarily unusual. Think about what Earth actually has going for it. We orbit a relatively stable middle-aged star that does not blast us with lethal radiation. We have a large moon which stabilizes the axial tilt of our planet and keeps our seasons from swinging into chaotic extremes. We have a Jupiter-like planet in the outer solar system that acts as a gravitational vacuum cleaner, intercepting many of the comets and asteroids that would otherwise pummel us into extinction every few thousand years. We sit in the quiet outer suburbs of our galaxy, far from the dense, radiation-soaked galactic center. We have plate tectonics, which cycles carbon through the atmosphere and regulates our temperature over geological timescales. We have a magnetic field strong enough to shield our surface from charged particles streaming off the sun. Each of those factors individually might be common enough, but together, as a package, the probability of all of them occurring simultaneously on a single planet may be extraordinarily small. The universe may be full of worlds where life got started, only to be sterilized by a nearby gamma-ray burst, or frozen when the planet lost its ability to regulate its own temperature, or bombarded into oblivion without a Jupiter-like guardian sweeping the outer solar system clean. On this view, simple microbial life might be widespread, but the chain of contingencies required to produce complex, multicellular, eventually intelligent life is so long and so improbable that Earth could be genuinely rare, perhaps even unique within the observable universe. But let us say we reject that pessimistic framing. Let us say life is common, and intelligence arises reliably wherever complex life persists long enough. We then run straight into a second and perhaps even more sobering barrier. The sheer scale of the universe makes physical contact, even radio contact, almost impossibly difficult from a practical standpoint. Here is an analogy that I find captures the problem beautifully. Imagine you are standing in the middle of the Sahara Desert holding a single grain of sand. That grain represents the volume of space within which we have conducted meaningful searches for extraterrestrial signals. The entire desert surrounding you represents the observable universe. Our searches, even our best and most sustained ones, have covered an infinitesimally small fraction of the total volume of space at a tiny fraction of the possible frequencies over a cosmically negligible slice of time. The SETI program, the Search for Extraterrestrial Intelligence, has been scanning the skies for radio and optical signals since the early 1960s. And while it has grown enormously in sophistication, the honest assessment is that we have barely scratched the surface of the search space. A civilization that chose not to broadcast on the frequencies we have prioritized, or that uses communication methods we have not yet conceived of, or that transmits signals too weak for our current instruments to detect, would be entirely invisible to us. Absence of evidence, in this case, is emphatically not evidence of absence. There is also a profound timing problem embedded in the structure of physics itself. Even if two civilizations exist simultaneously in the galaxy, and even if both are broadcasting powerful signals in every direction, the probability of those signals overlapping in time and space, given the distances involved, is genuinely small. Light travels at approximately 300,000 kilometers per second, which sounds fast until you realize that the Milky Way galaxy alone is roughly 100,000 light years across. A signal sent from a civilization on the far side of our galaxy right now would not reach us for 100,000 years. A response from us would take another 100,000 years to arrive. The conversation would span 200,000 years, and that is within our own galaxy. The nearest large galaxy, Andromeda, is approximately 2.5 million light years away. The timescales involved make meaningful two-way communication across intergalactic distances essentially impossible within the lifespan of any civilization we can imagine. And this brings us to what may be the most unsettling possibility of all, a possibility that physicists and astrobiologists have come to call the Great Filter. The idea, first articulated seriously by economist Robin Hanson, is this: somewhere in the sequence of steps that leads from dead chemistry to starfaring civilization, there is a step so difficult, so improbable, so catastrophic in its failure rate that almost nothing makes it through. That step is the Great Filter. The question that should make every thoughtful person pause is not whether the Great Filter exists. Given the silence of the cosmos, it almost certainly does. The question is whether the Great Filter lies behind us or ahead of us. If the filter lies behind us, then we are the lucky survivors of a near impossible gauntlet. Perhaps the emergence of life from chemistry is the hard step, occurring only once in trillions of worlds. Or perhaps the evolution of the eukaryotic cell, the complex cell with a nucleus that forms the basis of all multicellular life, is the bottleneck. The fossil record on Earth suggests that prokaryotic bacterial life existed for roughly 2 billion years before the first eukaryote appeared. 2 billion years of waiting for a single extraordinary evolutionary innovation. If that step is the filter, then intelligent civilizations are genuinely rare. The silence makes sense, and we are among the first. In that scenario, the vastness of the cosmos is simply ours to explore. But if the filter lies ahead of us, the implications are almost too dark to sit with. It would mean that the emergence of intelligent life is actually not that difficult, that civilizations arise with some regularity across the galaxy, and that they are then destroyed by something, a challenge or a catastrophe or a self-inflicted wound, before they ever manage to spread beyond their home system and become visible to the rest of the universe. This could be the runaway development of technology that outpaces wisdom. It could be the inevitable thermodynamic limits of civilizations that grow their energy consumption exponentially on finite worlds. It could be a biological vulnerability, a pandemic triggered by the complexity of their own biotechnology. Or it could be something we have not thought of yet, some phase transition in the development of intelligence that most civilizations do not survive. The disturbing implication of this second scenario is that the silence is not a quirk of timing or a limitation of our search techniques. It is a signal that tells us something profound about the fate of intelligence in this universe. And in that reading, the discovery of simple microbial life on Mars or Europa or Enceladus would be not a triumph, but a warning, because it would mean that life is common, that the early steps are easy, and that the filter, therefore, lies ahead of us rather than behind us. There is a further layer to this puzzle that touches on some of the most speculative but genuinely serious corners of modern physics. We tend to assume, without really examining the assumption, that a sufficiently advanced civilization would make itself known, that it would broadcast, that it would build structures detectable from light years away, that its energy consumption would leave a thermodynamic signature visible across the galaxy. Freeman Dyson famously proposed that a civilization harvesting all the energy of its star would surround that star with a shell of structures, creating a distinctive infrared signature. We have looked for these Dyson spheres. We have not found them. But the assumption that underlies the search, the assumption that a civilization will want to be found, may itself be deeply flawed. Consider what happens to a civilization as it grows in technological sophistication. At some point, the computational resources available to it become vast enough that the interior life of that civilization, its simulations, its virtual experiences, its inner universe of generated complexity, may become far more compelling than the physical universe outside. A civilization that has reached a certain technological threshold might choose collectively and rationally to turn inward, to invest its energy not in expansive colonization of cold and empty space, but in the generation of ever richer inner experience. In this framing, the silence of the universe is not evidence of absence. It is evidence that civilizations, when they mature, become quiet. They go dark not because they died, but because they chose a kind of depth over breadth. This is sometimes called the transcension hypothesis, and while it remains speculative, it is grounded in a real feature of how complex systems tend to evolve. The history of technological development on Earth shows a consistent pattern of miniaturization, of doing more with less, of finding that the richest complexity is often found not at larger scales, but at smaller ones. The transistor replaced the vacuum tube. The microchip replaced the room-sized computer. The most powerful information processing we know of happens inside biological neurons that are invisible to the naked eye. There is no obvious reason why this trend would reverse for a sufficiently advanced civilization. And if it does not reverse, then the most advanced minds in the universe may be invisible to us precisely because they are operating at scales and in modes that we cannot currently detect. What all of this adds up to is something genuinely humbling. The impossibility of finding intelligent life is not a simple statement about physics or biology or the size of space. It is a statement about the convergence of a dozen different barriers, each one capable on its own of explaining the silence, but taken together forming a kind of cosmic quarantine around intelligence itself. The distances are too vast for physical travel on any reasonable timescale. The timescales of communication at the speed of light are too long for meaningful dialogue across galactic distances. The window of opportunity for two civilizations to overlap in both time and technological development is narrow. The internal pressures on civilizations may drive them into silence long before they become visible to the wider universe. And the very step of producing intelligence from biology may be so improbable that we are, in all honesty, likely to be alone within any volume of space we can realistically ever explore. None of this means we should stop looking. The history of science is a history of being wrong about what is impossible. But it does mean that the silence of the cosmos is not a puzzle with an easy answer. It is telling us something real about the structure of reality, about the relationship between complexity and time, about the strange position that intelligence occupies in a universe that is overwhelmingly composed of things that do not think, do not reflect, and do not reach out across the dark to ask whether anyone else is there. We may be standing at the edge of an ocean so wide that light itself takes billions of years to cross it, listening for a voice that is either too far away to hear, too different to recognize, too quiet by choice, or simply not there. And the weight of that possibility, the possibility that in all of this staggering immensity of space and time, the emergence of a mind that can ask these questions is genuinely rare, perhaps the rarest thing in all of existence, is not a source of despair. It is, if you are willing to let it be, a source of the most extraordinary sense of responsibility. We are the universe becoming aware of itself. And if we are doing so in near solitude, then what we do with that awareness matters more than we have yet allowed ourselves to fully believe.